Welcome student in Christchurch Convent Digital Classes, subject chemistry, class 11th, chapter 2. So we will continue in this video about electronic configuration. In last video we have also seen the rule related to write electronic configuration. There are 4 rules: N plus L rule, Above principle, Pauli's exclusion principle and Hund rule are applicable when we write a electronic configuration. Now the electronic configuration of the element sodium is given to you on the right hand side. Sodium is 1s2, 2s2, 2p6 and 3s1. To argon 1s2, 2s2, 2p6, 3s2, 3p6. Follow the exactly the same pattern as the element from lithium to neon, with the difference that 3s and 3p orbital are getting filled now. This process can be simplified if we represent the total number of electrons in first two cells by the name of element neon. So if we write neon in big bracket, that means up to 10 means 1s2, 2s2, 2p6 configuration is completed. Then the electronic configuration of the element from sodium to argon can be written as, for sodium, Na, Ne, 3s1. So Ne contains 1s2, 2s2, 2p6. To argon, Ne means 10 electron, means 1s2, 2s2, 2p6 and 3s2, 3p6. The electrons in the completely filled cells are known as core electrons, and the electrons that are added to the electronic cell with the highest principal quantum number are called valence electron. You can see in the left hand side paragraph. For example, the electron in neon are the core electron, and the electron from sodium to argon are in the valence electron. In potassium Ka and calcium Ca, the 4s orbital being lower in the energy than the 3d orbital, so is occupied by 1 and 2 electrons respectively. So a pattern is followed, beginning with the scandium, means the atomic number 21, the 3d orbital being the lower in the energy than the 4p orbital is filled first. Consequently, in the next 10 element from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc, the 5 3d orbitals are progressively occupied. We may be puzzled by the fact that chromium and copper have 5 and 10 electrons in the 3d orbital rather than 4 and 9, as their position would have indicated with the 2 electron in the 4s orbital. The reason that fully filled orbitals and half filled orbital have extra stability, that is lower energy. Therefore, P3, P6, D5, D10, F7, F14, etc. configuration, which either are half filled or fully filled, are more stable. So chromium 24 and copper 29 adopt 3D5 and 3D10 configuration. So these are the exception do exist of the electronic configuration rule. Now with the saturation of the 3d orbital, the filling of the 4p orbital starts at gallium and it's complete and is complete and is complete at krypton 36. In the next 18 element from rubidium to xenon, the pattern of filling the 5s, 4d and 5p orbital are similar to that of 4s, 3d and 4p orbitals as discussed above. Then comes the turn of the 6s orbital in cesium metal. The barium, this orbital contains 1 and 2 electrons respectively. Then the lanthanum to Mercury, the filling of the electrons take place in 4f and 5d orbital. So after this, the filling up of 6p and then 7s and then finally 5f and 6d orbital take place. The element after uranium are called short-lived, and all of them are produced artificially, that is when they are totally prepared in chemical lab. The electronic configuration of the known element as determined by the spectroscopic method are tabulated in table 2.6, page 66. One may ask, what is the utility of knowing the electronic configuration? The modern approach to the chemistry in fact depends almost entirely on the electronic distribution to understand and explain chemical behavior. For example, questions like why two or more atoms combine to form molecules, why some elements are metal, others are non-metals, why elements like helium or argon are not reactive. So all the answer of this question can be understood with the help of electronic configuration or electronic structure of atom. Now 2.6.6 Stability of completely filled half filled subcell. The ground state electronic configuration of the atom of an element are always corresponds to the state of the lowest total electronic energy. The electronic configuration of the most of the atoms follow the basic rule given in section 2.6.5. However, in certain elements such as copper or chromium, where the two subcells 4s and 4d differ slightly in their energies, electrons are shifted from a subcell of lower energy 4s to a subcell of higher energy 3d. Provided such a shift result in aura orbitals or subcell of higher energy getting either completely filled or half filled, the valence electronic configuration of chromium and copper, therefore 3d5 4s1 and 3d10 and 4s1 respectively, and not 3d4 4s2 for chromium and 3d9 4s2 for copper. It has been found that there is a extra stability associated with these electronic configuration. So causes of the stability of filled and half filled subcell. The completely filled and completely half filled subcells are stable due to the following reasons. First, symmetrical distribution of electrons. It is well known that symmetry leads to stability. The completely filled or half filled subcell have symmetrical distribution of electron in them and are therefore more stable. Electrons in the same subcell here 3D have equal energy but different spatial or distribution or orientation. Consequently, their shielding of one another is relatively small and the electrons are more strongly attracted by the nucleus. Second, exchange of energy. The stabilizing effect arises whenever two or more electrons with the same spin are present in the degenerate orbitals of a subcell. These electrons tend to exchange their position and the energy released due to the exchange is called exchange energy. The number of exchange that can take place is maximum when the subcell is either half filled or completely filled. So as a result, the exchange of energy is maximum. So is the stability. So you may know that note that the exchange of energy is at the basis of the Hund rule that electrons which enter in the orbital of equal energy have parallel spin as far as possible. In other words, the extra stability of half filled and completely filled subcell is due to relatively small shielding, and secondly, smaller coulombic repulsion energy, and the third is larger exchange energy. So This much in the present video. You can see that table 2.6 here. Electronic configuration is given to you of the element from hydrogen to strontium up to 111. So this much in the chapter 2. We'll start chapter 3 in the next video. Thank you for watching. See you in the next video.